Good afternoon, everyone. Hope you had a good break. I'm Pankaj, and I'm joined by my colleague Punakshi here. We are engineers working for the service mesh team at Intuit. We are excited to share our journey through autoscaling Istio at Intuit. We'll specifically talk about how and why we had to switch from a basic resource-based autoscaling to a more nuanced connection-aware autoscaling for the Ingress Gateway component at Intuit. This was done to essentially cater to diversity of the workloads at Intuit. So we'll dig deeper in those topics. So here's a quick look at what we are going to cover. I'll talk about the state of Kubernetes at Intuit, the scale, and the kind of services we support. The service mesh architecture, we'll walk through how in our service mesh architecture, the request flows from a source cluster to a destination cluster and the various hops in the middle. The scaling issue, we'll dig deeper into the scaling issue we faced with Ingress Gateway and mostly related to the traffic patterns we have with the various workloads at Intuit and also multi-tenancy, the AWS CLB specifically. And then we'll finish with the solution, what worked for us and what we achieved as a result of this solution. So for those who don't know about Intuit, Intuit is a global financial technology company, and we are developing an AI native platform which caters to 8,000 plus technologists at Intuit and supports our suite of products like TurboTax, Credit Karma, QuickBooks, and MailChimp. And we have approximately 100 million customers that are using these products actively. So Intuit is also a heavy user of the open source technologies, and we are excited to be here to give back as part of our commitment to the open source community. A little bit more about the dev platform that we have at Intuit. This developer platform enables the engineers across Intuit to develop code in a fast, secure fashion. And it delivers the experiences all the way from the app configuration, the runtime, the traffic management, and also handling the operations. This is supported by 350 plus Kubernetes clusters in production that run about 3,000 services. Now that we understand the scale of Kubernetes that we use, I would like to talk about the service mesh at Intuit. So we have service-to-service communication, east-west communication, happening through service mesh, and this is the Istio service mesh. And Istio is installed on each one of those 350 plus clusters. Important thing to note here is that 90% of our cross-cluster, 90% of the traffic is cross-cluster on mesh, and this is done mainly to handle scenarios like HADR, fault isolation. Sometimes we have to respect the cross-organization boundaries. So we have done it this way. That's why majority of the traffic is cross-cluster. And the service mesh also powers the products like QuickBooks, MailChimp, TurboTax. So the service mesh stability at Intuit impacts directly the millions of users that are users of these products. Apart from the scale, there is also a high degree of variability among the workloads that we run. On the screen, if you see, like during the peak load, this OIGQL is one identity GraphQL, one Intuit GraphQL. So this service calls other services and uses GraphQL to do that. On this cluster, we receive 206K TPS, while majority of our clusters run low TPS volumes, like less than 100 TPS. Also, the workloads have unique requirements when it comes to the service times. Some workloads require us to hold connections all the way up to 35 minutes, while most of the requests are fulfilled within below 3 seconds. So this combination of the scale of managing so many clusters, as well as the variability in the workloads, makes one-size-fits-all auto-scaling solution nearly impossible. So to understand the problem that we face with the scaling a bit better, let's dive deeper into the architecture that we have. So we run a global mesh global control plane, which is comprised of our in-house mesh management tools like Admiral and Cartographer. They essentially deliver cross-cluster connectivity at Intuit. So here, the cluster A talking to cluster B, the cross-cluster communication happens over transit gateway. And we also have our internal certificate generator, which is responsible for minting out certificates to all the workloads for Istio MTLS. So this picture shows Admiral that watches Istio and Kubernetes resources in all the clusters, and then configures the Istio proxies that are running as sidecars in each and every cluster. So we are running in the sidecar mode right now. So here we'll go through the various hops that a given connection goes through when it tries to go from source cluster on the left to the destination cluster on the right and the workload running there. So when a client connects to the classic load balancer via the transit gateway, the classic load balancer then may send the request to one of the registered EC2 instances that is running the Ingress Gateway pods. And then kube proxy redirection may cause that request to land on a different EC2 node where the Istio Ingress Gateway receives the request and then forwards to the destination proxy. So this entire communication, starting from the client proxy to the destination proxy, is encrypted using MTLS. So we have end-to-end MTLS. So just to highlight a few details about the kind of architecture that we have and the integration components, which we will go back to when we explain the problem and the solution. So CLB is fronting the Istio Ingress Gateway pods. We run 2 containers per pod, Istio proxy to intercept the traffic, and the cert agent wrapper, which is for certificate management and automatic rotation of the certificates. We do that at predefined intervals based on the application requirements. Ingress Gateway, and this is important, Ingress Gateway is running in TLS pass-through, so we do not terminate TLS on the Ingress Gateway. So it's just acting as a TCP proxy where the MTLS ends at the destination proxy. This means we do not have any L7 visibility, and the CPU load that we see on Ingress Gateway does not necessarily correlate to the traffic stress that the backend systems are experiencing. Regarding the integration layers, we have transit gateway for connectivity and components like Admiral and Cartographer. They orchestrate multi-cluster service discovery and also configurability. And as I spoke about earlier, a single cluster is running multiple workloads. So in the critical clusters, a single misbehaving Ingress Gateway pod could cause issues for the other pods as well. So now I'm trying to dive deeper into the core problem that we faced. So this diagram shows the AWS CLB, which has a connection queue in case the backend pods are overwhelmed. What we saw was our clients, they reported getting 503s, intermittent 503s. And when we tried to investigate that issue, we saw that we got a spike of connections on the CLB, followed by the queue piling up. And then subsequently, the CLB starts to drop any connections because it's not able to accept anymore. So this resulted into 503s on our client side. Some of them did get fixed with the retries, but mostly this 1024 limit was reached within a minute, and we would have an impact. So with this, we started exploring what was causing issues on the Ingress Gateway layer. But when we looked, sometimes we would see little CPU spike, but mostly the Ingress Gateway pods would be running fine with the thresholds not crossing at all. So in a sense, the system was not scaling to meet the requirements. The next question, of course, is why the pods were getting overwhelmed, when the HPA metrics were underutilized? The answer was in how we were actually scaling. So I would pass it on to Punakshi, who would go over the details of the problem, the intricacies of the algorithm that we used, and the solution that worked for us. Over to you, Punakshi.
Okay. Hello. Yeah. Cool. So now we'll look at the metrics that were actually part of the Istio Ingress Gateway HP. They were very basic ones initially. We had CPU as well as memory, and both of them were running at the 60% target. But once we evaluated our different workload profiles, what we saw was that most of our services had service times, the transaction time, that ranged between a couple of seconds and not just a few milliseconds. So how that translated onto CPU was that even though the TPS was increasing, but because the rate of opening and closing of connections wasn't so aggressive, it was not translating onto CPU enough for it to cross the 60% threshold. Now, these active connections were indeed increasing the memory, but the memory was actually not tuned to in accordance to the active connections. Rather, it was tuned in accordance to the Istio configuration that Ingress Gateway needed to facilitate the routing within that cluster, be it through service entries, destination rules, virtual services. Along with that, we had another requirement that on like our very high TPS clusters like identity, OI, GQL, we saw they have very aggressive ramp up requirements that they could go from like tens of TPS to 200K TPS within a 2-hour period. So to like solve for the CLB 1024 problem that Pankaj mentioned, and to handle this aggressive ramp up case, what we had to do to mitigate this issue in the short term was that we had to manually intervene and over provision our Istio Ingress Gateway pods. But then this obviously meant that we were wasting a lot of money there. We were spending a lot of money on our cost. Now, this problem did come with a lot of infrastructure constraints as well, and they had different nuances. Like we discussed, that the overwhelming of Istio Ingress Gateway can lead to the 1024 issue. Similarly, if the CLB in itself gets overwhelmed, then we can see the same symptoms, and that can easily happen for the aggressive ramp up use case. And because of that, in the short term, what we could do is that we could pre-warm the CLB nodes, but again, that would add on to the cost even further. So the long-term solution would have been to actually migrate onto NLB, and that's what we did on most of our clusters. But again, on the high TPS clusters, we encountered another challenge that for those clusters, we were actually hitting the transient subnet IP limits. And what that meant was that we couldn't run the classic load balancer and the network load balancer in parallel so that we could do a gradual cutover of the traffic onto NLB. Through our testing, we also found out that the EC2 nodes themselves have like a choking point that there are only 28,000 or so of Emerald ports that are available. So that kind of puts a upper limit to the consecutive active connections we could have from that certain EC2 node. And we wanted to be cognizant of the fact, like heed caution to the fact that NLB in itself doesn't provide SNI routing. So when we have to send the traffic onto our different destination workloads, we have to do it through Ingress Gateway and can't be done through NLB directly. AWS in itself has published a number onto their limits of NLB. A certain NLB can only make 55,000 connections to a certain target within a minute. So having evaluated all these different constraints, what we knew was that definitely connections is the key that we need to pay attention to. And it's not just about the rate at which we are opening connections or closing connections. We also need to pay attention to how long a certain connection is open. Only then we'll be able to scale better. And how it translated onto transactions was, At least in our case, we have a static hard-coded value in our destination rules where we have configured that for a certain connection, we serve only 5 requests, and then we churn the connection and return it back to the connection pool. And through our testing, we found out that for our most average use case where the requests are like ranging between 2 seconds or so, from a certain Ingress Gateway pod, we could serve around 10,000 K active connections before we had hit saturation. Now you might ask that MRPC 5 sounds like a very low number, and it is indeed low, but for Intuit, there are many services which are very, very sensitive to the load balancing they experience. They expect that, especially the low TPS service and as well as couple of high TPS as well, that when the new pods are coming up, they expect them to take traffic as soon as possible, especially in the Kinry deployment use cases. So through our testing, what we found out was that 5 is kind of an optimal value where we are not doing handshake for every odd request, but we are able to have even load balancing across the pods without having a very large skew, even though the service might in itself be a low TPS service. So having set the problem landscape, having been aware of the constraints, let's move on to the solution and what are the actual objectives that we are looking for in the solution. So first is definitely resilience. We want to get rid of any 503s, 504 errors. We want to support the gradual ramp up as well as the fast ramp up. We want to optimize on the cost. And along with that, we want to support one more use case, which we saw for a couple of our services where they didn't have a consistent load pattern all the time. They didn't have consistent traffic, but they received traffic in spikes. So we wanted to support this as well without having to pre-scale our ingress throughout having to waste so much of money. So to solve, like we discussed for the ramp ups, obviously the connection was the key. We could solve for the different kinds of ramp up using the active connection metric. But let's discuss a little bit more on the spike absorption case, how we solve for that. So for that, the metric that we went for is a curved metric. This formula, although definitely it's not very intuitive, but we came through this just through empirical testing. And what we found out was that the more number of pods we have, more number of ingress pods we had, the more easily we could absorb the spikes. So what that meant for scaling was that whenever we were running low number of pods, we had to scale a lot more aggressively. And later down the line, when we are running larger number of pods, even if there is a spike at that time, we can scale a lot more gradually and it'll still be fine. So we did a couple of our tests through our empirical testing. We fed that data into AI and we got this non-linear formula, which definitely doesn't look very intuitive. But essentially what it is doing is it's relying on the the connection rate, that is the rate at which we are opening or closing connections. We are looking into the pass window of say 1 minute and relying on the pod count, that the Ingress Gateway pod count that we started with. So what this metric will give, that let's say if you started with 6 pods, it will scale a lot more aggressively because the curved metric value will be much higher when the pod count is lower. And accordingly, you can just put this metric into the HPA and do aggressively scale at the start, but prevent any oscillation that you are scaling very often and then scaling up again. Now, if we see at this formula again, it still doesn't account for the duration of the connection that we looked at. So this metric in itself didn't solve all of the problem. So we knew that we have to go for a hybrid approach kind of scenario, where the CPU would be the key for the for the fast requests, for the gradual ramp up, fast ramp up, as well as for slow ramp up scenarios. We have to rely on active connections, and to absorb onto the spikes, we have to rely on the curved metric. And that in itself would be the kind of the complete solution. As what exactly was the active connection metric, it was the downstream CX active from Envoy that comes out of the box. Why we could use downstream and not the upstream? That comes from the fact that Istio Ingress Gateway in our case is just a pass-through. So it was indeed a one-to-one mapping between the downstream connections and the upstream connections. And then rest, like we discussed, that the CPU and curved metric were definitely essential to what we were doing, and we wanted to keep that to optimize on the cost. Now, talking further on the cost, like we mentioned that most of our clusters actually have either they have less number of mesh-enabled services or they have less TPS. And they might not have that aggressive of a ramp-up requirement as well. So what that meant was that we could have lower number of CPU allocation, resource allocation there, and it would still work fine. So we decided on a dual tier kind of scaling policy to avoid spending a lot on cost. For the like default tier, we had one CPU, which meant one concurrency. And there we kept the active connection target a little lower. We kept it as 3,000, so that that becomes the primary metric, because those services are a little slower. So we'll rely on this active connections metric to scale a little faster there. And for the override tier, that's mostly for our identity, MailChimp, OIGQL services. We have concurrency of 3. We have allocated 3 CPU there, and they have a lesser target on CPU because these are fast requests, so they can scale more on the CPU. But for the fallback scenario, we still have active connections, which we have configured around 66,350 on most of our clusters, on most of our override tier clusters, so that if they experience any slowness, they're still able to scale. So keeping that in mind, and because we pay for nodes and we don't pay for pods, the same two tiers strategy was employed onto the nodes as well. That for the smaller tier, the default tier, we went with XL nodes, and in some cases even M6A large nodes. But for the override tier case, we went with bigger nodes, keeping in mind that we have less pod density, so that just in case if we lose a node just because of hardware failures, software failures on AWS end, we don't lose a lot of Ingress Gateway capacity. And like for the override tier, usually we went for M6A 4XL large nodes, unless the memory requirements on those clusters were even larger, and we optimized it accordingly. As from the how did the overall results look? So we were able to, like with just 67 pods running with 3 CPU and less than 30% of CPU usage, CPU utilization of these pods, we were able to support the aggressive scale up. We could go from 0 to 216K TPS, and no 503s occur, no 504s, no dropped connections. And we were able to like do that very gracefully. So the like kind of a TLDR of this presentation is that for shorter service times, definitely CPU is our friend. For longer service times and for slower churn of connections, definitely we have to look at active connections. And if we have use cases like that of having spike bursts, then we need to look at curved metrics and employ that in the HPA wherever required. And we just have to think about not just about how often the connection is being opened, but we need to see how hard every connection is working to actually to be able to scale gracefully and get the intended result that we want. So just thinking about the problem that Pankaj had mentioned, were we able to solve everything we like kind of wanted to achieve? So definitely we were able to achieve the responsiveness from the HPA in accordance to the TPS that we wanted. We were able to reduce our manual overhead that we were like every engineer had to do to manually provision the clusters, decide on its HPA, look at the nodes, whether nodes will be able to scale or not. We were able to achieve reliability, no client errors occurred. And from cost perspective also, just because we were able to decide on the node density, reduce the number of nodes we had, we were able to optimize on the node, and we removed the over provisioning overall. And hereafter, hopefully, we are hoping that we live happy from here on. So thank you, everyone. We'll expect you to see you on the on our Intuit booth. We are big into open source, so we have some great NUMA flow related demos prepared. Expect to see you there. Very excited. Thank you. Questions? Thank you.
Cool. Thank you. Oh, yeah.
Oh, sorry.
Do you think that node port routing could be a problem? Do you still use it?
No, we like in our like you want to answer?
Go ahead. Go ahead. So your question is specifically if the request does not go to node port and then uses service IP, is that what you're hinting at?
Yeah, specifically for like for the ALB, it could hit the pod and it could hit the pod directly, right?
Yeah, the ALB can, but the CLB cannot. And the classic load balancer does not have the L7 visibility, so it cannot. And with NLB also, we are achieving hitting the Ingress Gateway pod directly. We explored that option as well. But there are, and we are also exploring probably moving to ALB as well, which can terminate TLS there so that we get some L7 visibility. So that all that is still work in progress. But yeah, for now, this solution is working for us because we were using node port to begin with. So we wanted to make minimal changes to achieve what we did. Yeah. Thank you. Yes.
Are you considering switching to ambient mode instead of sarcasm?
Ambient, not really, because I think in the last KubeCon we discussed the ambient is still not GA.
And it's
right?
not ready for migration, I think. Like, just from what we heard was that if you're adopting mesh new, then definitely that's the way to go. But for migration, given that our scale is so huge, we're still a little like nervous that how we, given our variability, like we have 35-minute requests as well. How would that sustain from waypoint proxy and all? We're a little nervous about it still. And given that the migration path is still not clear, definitely we're exploring that option, trying out some options internally. But
yeah, we have done some experiments.
Yeah.
Yeah.
Thank you.
Anybody else has questions? All right. Thank you all.